Here's a story about mathematical deduction that I love, mainly because it is true and because it had an impact, albeit small, on the outcome of the Second World War. It is the story of how a simple statistical formula successfully estimated the number of tanks the enemy was producing at a time when this could not be directly observed by the Allied spy network. By 1941 and 42, the Allies knew that U.S. and even British tanks had been technically superior to German panzer tanks in combat, but they were worried about the capabilities of the new Marks 4 and 5 tanks. More troubling, they had really very little idea of how many tanks the enemy was capable of producing in a year. Without this information, they were unsure whether any invasion of the continent on the Western Front could succeed. One solution was to ask intelligence to guess the number by secretly observing the output of German factories, or by trying to count tanks on the battlefield. Both the British and the Americans tried this, but they found that the estimates returned by intelligence were contradictory and unreliable. Therefore, they asked statistical intelligence to see whether the accuracy of the estimates could be improved. The statisticians had one key piece of information, which was the serial numbers on captured Mark 5 tanks. The statisticians believed that the Germans, being Germans, had logically numbered their tanks in the order in which they were produced, and this deduction turned out to be right. It was enough to enable them to make an estimate of the total number of tanks that had been produced up to any given moment. An estimator or point estimate is a sample statistic used to estimate a population parameter. In this case, we are trying to estimate the maximum tank serial number based on our sample of tanks. How could you use the serial numbers from our sample to estimate the maximum number of tanks in the population? So I had a bag of pseudo tanks, actually bottle caps that were numbered sequentially, and I had students select a sample, a random sample by reaching in the bag of those tanks, and here are the serial numbers that we got. Now we could compute a lot of sample statistics from this sample. We could find the mean of the sample, we could find the median, the standard deviation, the range, the maximum, the minimum value, the IQR, Q1, Q3, and we could combine those in any combination or create a completely new statistic of our own. So some suggestions that the class had this year and in the past are, let's take the mean and add 2 standard deviations to it. Seems logical based on the normal model that might get us close to the maximum. Or take the maximum and add 1 standard deviation, because the maximum of the sample is probably smaller than the maximum of the population. Maybe adding 1 standard deviation would get us the true maximum. Maybe 2 times the median, since the median is the middle number. If we doubled that, maybe we'd get the maximum. Or maybe take the maximum and add the minimum to it on the assumption that the minimum is a certain distance from 0. Maybe if we add that same distance from the max to the sample maximum, we would get the true maximum. So those are all possible ideas, but how do we know which of those ideas might actually provide the best estimate? And this is where statisticians do a simulation. First of all, the statistician would create a hypothetical population containing a known number of tanks. So for example, in class we did 500. Then we would take many random samples of the same size from the numbers 1 to 500. For each sample, we would compute the same statistic, one of those ones that we are testing out to see how good it is. So we're going to compute the same statistic, graph the distribution then of all the sample statistics, then repeat that process for each of the statistics that we're testing. If the distribution is centered at 500, then the statistic is considered an unbiased estimator of the sample maximum, because the statistic does not consistently overestimate or underestimate the true population maximum. So now we're going to take a look at some of the statistics that have been tested over the years in my class and look at the distribution of those sample statistics and see whether or not they are unbiased estimators. The blue line in these graphs represents the true population maximum of 500. The first statistic we're looking at is 2 times the mean plus 1 standard deviation. Clearly not an unbiased estimate estimator. It overestimates the true population maximum by a great deal and does so very consistently. Also, this is also true of the mean plus 3 standard deviations. The mean plus 2 standard deviations is much better. Its center is fairly close to the true population maximum of 500, but it does tend to overestimate a little bit more than it underestimates, but we could consider this pretty close to an unbiased estimator. Also, 2.12 times the mean. Not sure why the student came up with 2.12, but I guess they decided the mean was the middle of the sample, and so if you doubled the mean, you would get close to the maximum of the sample, and then, but if you doubled it on a little bit more, then maybe that would be the maximum of the population. Not a bad idea. It seems to be centered fairly close to 500, so this could be considered an unbiased estimator. Now you may be wondering at this point, okay, maybe it's an unbiased estimator, but there's sure a lot of sample maximums that are very far from 500. It was estimating anywhere from 300 to 800. So is that really a good estimator? Well, you brought up a fair point. We have to take into consideration two things. First of all, is it unbiased? Does it center at the true population maximum, neither overestimating or underestimating consistently? So in other words, if it overestimates sometimes and underestimates sometimes, but basically is centered at the true population maximum, then we consider it unbiased. But it's still not a very precise estimate because there's a lot of variability. So variability is something else we have to take into account. So let's look at a few more. This is 1.05 times the maximum. Notice we have a lot less variability here. However, it looks like we do have some issues with underestimation, but this is not too bad. It seems to underestimate by about 100, which was less than what we had before. Q3 plus 1.5 times the IQR, remember the fence rule for determining outliers, definitely is biased. It consistently overestimates the maximum. The median plus the IQR and 2 times the mean are both very good. They both are unbiased estimators, centered very close to, if not at, the true population maximum. But once again, both of them have a significant amount of variability, varying plus or minus 200 from the actual maximum. So what did the statisticians in World War II actually use as their statistic? It turns out that this is the real one. Notice not only is it's the mean of the distribution centered almost exactly at the true population maximum, but the variability is extremely small, basically plus or minus 40 at the most. Like it could go as low as 40, at 40, 50 maybe, higher. It's only overestimating by about 20 at the most. Notice also that the majority of the time it would if it did overestimate, it's going to overestimate by not a whole lot. So this one would be the best for two reasons. I didn't write them down, but I'll just say, number one, it's an unbiased estimator. It's true, its mean, the mean of all the sample maximums, is centered at the true population maximum, and it has very little variability. So what is this statistic? Well, this is something that you would never have guessed. You take the maximum minus 1 times the sample size plus 1 divided by the sample size. Well, this actually makes sense. Take the population maximum. I'm not sure why they subtracted 1. I'm guessing that that was just a little correction to make the model more accurate. But if you take the sample size plus 1 divided by the sample size, you're multiplying the sample maximum by a number that's slightly bigger than 1. The smaller the sample size, the bigger this number will be. So for example, if you had a sample of size 4, this number would be 5/4, 1.25. But if you had a sample size of 10, this number would be 11/10, or 1.1. So the bigger the sample, the less corrective power we need when we multiply this. So it turns out that this was extremely accurate. So here's the rest of the story. Using this formula, statisticians reportedly estimated that the Germans produced 246 tanks per month between June 1940 and September 1942. At that time, standard intelligence estimates had believed the number was far, far higher, at around 1,400 per month. After the war, the Allies captured German production records showing that the true number of tanks produced in those 3 years was 245 per month, almost exactly what the statisticians had calculated, and less than 1/5 of what standard intelligence had thought likely. Emboldened by this estimate produced by the statisticians, the Allies attacked the Western Front in 1944 and overcame the panzers on their way to Berlin. And so it was that statisticians won the war, in their own estimation at any rate.